Okay, so welcome everyone, also from my side. My name is Alexander. I'm a PhD student here in the group of Christian, and I have the opportunity today to tell you a little bit about multiphase flow. Or I tried to scratch the surface actually on multiphase flow for the lattice-Boltzmann method, because actually it's probably quite a rabbit hole, but you will understand that in a second. And I tried to give you a brief overview of what is possible, and yeah, just tell you a little bit on how it works, as far as you learned, or I tried to base myself on what you just learned in the lecture before. So just just to define what I mean with multiphase flow in the end, I'm just always talking about fluids that are present in several phases, or just several fluid components that are in contact with each other. And there's these systems are everywhere around us. Reason for studying, I brought up a few examples, but that's nothing complete anyway. There are probably more examples that might also be more expressive, but I'm just a physicist, so I don't know all of that. So I mean, the example I brought up on the top left here is just about storing, in this case, the CO2, carbon dioxide storage, in order to somehow deal with the climate change. So the general idea in that is that when we burn fossil fuels for electricity generation, for example, then we release a lot of carbon dioxide. And one of the ideas to temporarily have a solution is to just capture the CO2 where we produce it and then just store it underground somewhere. That's basically depicted here. And when you're basically pumping it down somewhere to store it, that's exactly where you have such multiphase flow systems where there's some fluid down there usually, and you're trying to pump down the gas. And so you will have multiphase flow there, which you obviously want to study and understand very well before you do such things, because they are usually also very costly. And general such systems that are related to porous materials, which I try to depict here, are well known to or well studied with such multiphase flows. In this case here, these processes are usually referred to as imbibition or drainage. So if you have a porous material and it's filled, for example, with one fluid component, and you're trying to soak it up with another fluid, then you usually refer to that with imbibition, and you also have capillary effects there. And I mean, a more non-lab example for that would actually be on the top right here, which is a process related to recovery of oil. So I won't go into detail, but the idea is that you have some reservoir of oil in the ground and you're trying to extract that. And obviously your goal is to maximize the amount of oil you get out of there. And there are a whole lot of techniques on how you can do it and try to improve the yield you get out. And one of the ideas is, or one of the methods they do is just try to replace it with oil. And there are a lot of mechanisms that are not understood well. And there's also optimization necessary, or not technically necessary, but obviously seek for, because it's also related to a lot of money. And the last thing I showed here is in the process of waste management. And in general, this example is something that is a leftover from oil extraction. So when you do such processes, you can end up with such lakes of a whole lot, or a mixture of a whole lot of things, and you actually try to separate those. In this specific example, it actually exceeds multiphase flow because there are a lot of other difference present too. But separating all of these things takes a lot of time, and you want to speed it up. That's also something that is highly related to clearing, something that is called groundwater remediation, where you have contaminants in your groundwater and you want to extract them. and there's also like some applications of those. But I mean, that enough about the motivation. In general, what they all have in common, what I'm trying to tell you is like on top here, like the governing equation. I mean, you saw it already in the last presentation that when we're dealing with such systems on like the continuum scale, then what we're looking at is basically some formulation of the Navier-Stokes equation, usually the incompressible one, with the slight, with an additional term that wasn't introduced before, which is actually the surface tension. And that's basically the key point that we're trying to introduce now into the lattice-Boltzmann method. And like it consists of basically a quantity that is related to the materials we're using and the curvature of the interface, but also this contribution only exists in the interface. Like the technical details is not that important, or the mathematical details for this. The whole point is that we want to add another term that into our system. And yeah, I called it a zoo of models because that's more or less literally what it is. Like I brought you a picture that I slightly adapted from a continuous fluid dynamics modeling course. And I mean, basically what it tells you, or it shows you some models. Like it's obviously also incomplete, but the whole point is that there's several length scales you can simulate such problems on. On the very left, like you have a molecular scale to model this. Obviously, that's not what I'm going to talk about, but that also works. I'm going to talk about mesoscopic scale, so already continuum. But there's also like a macroscopic modeling scale, which is usually what the engineers typically look into. And like all of these models have a fairly specific application and like benefits and obviously drawbacks. And so a key question before you even start is that you need to ask yourself what you're even trying to model and which length scale is that on. And in general, for like I'm only going to talk about continuum from now on anyways, but there's like two types of models in the end. There's something that referred to as like diffusive interface models, and like something that the engineers called like interface capturing ones. The key difference is that you have on the diffusive interface models is you have a continuous transition between the phases. So you have some area where you have a mixture, basically, that might not be what is physically, or what you don't, or like you do, it might not have a physical background, but you do that because numerics becomes way easier and it's usually sufficient for modeling. Like with the interface capturing methods, you basically introduce like conditions, like jump conditions for several quantities, and they are usually way harder to solve numerically. And within the lattice-Boltzmann framework, I'm only going to talk about diffusive interface models. So we have continuous transitions between everything, and I will show you also pictures later on, like to properly make you understand, hopefully, what I meant with this. So I need to give you like a little bit of the terminology within the lattice-Boltzmann framework. I do that because literature is slightly different between engineers and lattice-Boltzmann people in the end. They use the same terms for different things, and I just want to clarify what within the lattice-Boltzmann community they mean. And I just want to differentiate between two things, like something called multi-phase and multi-component. So with what I mean with multi-phase is that you are simulating one chemical species in the end that is present in different phases. So you have like liquid vapor, like a liquid vapor interface, for example. And so you're numerically dealing with one set of fields. And usually these methods are significantly less expensive, but they are not as widespread. Multi-component in the lattice-Boltzmann method always means that you have several components present that are usually also immiscible. So in practice, one usually brings up such water oil examples. And that usually also means that you have like multiple sets of fields for different reasons, and you will understand it in a second. And that also makes them more expensive usually. But like if you go to productive or like if you go into literature and see what people use for certain things, then you will like 90% within the lattice-Boltzmann literature, you will find multi-component models. Although they just call it multi-phase sometimes too. It's always multi-component. Okay, so with that, I will finally go into the lattice-Boltzmann framework itself. And I will skip all the lattice-Boltzmann details. You heard about that before. And I'm just going to try to tell you what's the difference now, how to extend the lattice-Boltzmann method you see before to include multi-phase flow. And basically there are three flavors or like three different techniques you can use to achieve that. These are these three here: free energy, Shan, and color gradient. And I will try to tell you the gist of all three of them because they have very different fundamentals and like or ideas of how they build up and how they work. And they are also capable of simulating different systems actually. And I'm gonna start with the free energy one, which is actually also the actually the youngest model of all of those three. In the lattice-Boltzmann literature, we call it a top-down approach. The reason for that is that you basically start from thermodynamics and you're defining from the very high level what you want your system or how you want your system to behave. That will basically, or like a key property of that is that you by design are always thermodynamic consistent. And we can simulate both multi-phase and multi-component. So for the general, like the general gist of what you do in this method is that you start with literally sitting down and writing your free energy density you want to simulate in a system. So that, I mean, that usually in this model contains like two contributions that usually relate to the bulk phase and also like a gradient phase. Or like a bulk phase, sorry, and just a gradient term. I will bring up an example on the next slide too. And from that, you actually calculate a chemical potential, which will somehow be incorporated into the system. There are actually two flavors. You can directly manipulate the pressure tensor itself, which was, I think, not talked about before. It's also the more advanced technique. I will just restrict myself to the application of forces because it's more intuitive. Like mathematically they're equivalent. It's numerics in the end that make the difference. But like the whole idea is you think with yourself before you define what you want, and in the simulation you then actually calculate the chemical potential gradients to include forces. So in practice, you take a regular lattice-Boltzmann fluid you saw before, and you somehow apply a force that you also need to discretize somehow on the grid. And for a multi-phase flow, so one fluid component, as I said, with two phases, like you basically are seeking for a profile or like a system that somehow looks like or similar to that. So you have like one, or like on the one side of, or one position in the system, you have like a gas phase, and in another position a liquid phase. And with the diffusive interface model, it's exactly such a continuous transition area that you have. Like this will always be present, and is like a key property of all the methods I will tell you about. But like depending on the length scale you're at, that might be an unphysical property, and you only do it because of numerics. Like if you think like on a nanometer length scale, you will see such transition areas. But if you go to like centimeter scales, then obviously you won't observe this in like in the real world. And like I brought you here just an example of to show you that this thing looks, I mean, somewhat simple, but I don't think it's that educational. The whole point I showed to you here is that this model is actually not used in any production, but it's an educational model because you can calculate a lot of the quantities of interest beforehand or analytically. So you basically use it as a test case for your implementation, for example. And I mean, for the quantities, I just wanted to mention that the first part here is only related to the bulk phases, where the subset C would be the critical point. And usually for these type of models, you have always such a term here that is like a prefactor that is then related to the surface tension of your system and like some gradient dependence that basically penalizes the interfaces in your system. And I mean, I spared you with the actual chemical potential, but what you end up with is like in the simulation. So as I said, you just take a regular lattice-Boltzmann fluid and you calculate a force based on the local densities there. And what you can achieve is basically a plot like this here, and that for a certain set of the parameters you put into the simulation, you get like a separation of the phases with like a liquid gas ratio you are basically you set beforehand. Like as I said, these are not as prominent with the models. Like the more prominent case is the multi-component version. And actually, to extend this idea now for multi-component, it becomes a little bit more complicated. So the general difference now between multi-phase and multi-component is that you need to introduce an order parameter to indicate the components you're working with. Like the plot here on the top right looks very similar to what you have seen before. The whole difference is that on your y-axis, this time it's not a density, but it's an order parameter. And basically a value of -1 means that you're in one fluid, in the bulk phase of one fluid, and a value of 1 is the bulk phase of another fluid. Like this is a construction you do, and or like you define beforehand. Like it's and the range is also like something you can choose yourself, but it's just easier to do it in this range. And so I just tried to, in a simple system, you would just have like whatever, like a bulk phase blue associated -1 and the red one with +1. And to actually now introduce or like the quantity, or basically what was previously discussed is to have like a viscosity, or like you have basically in the end local viscosities in respect of with respect to the lattice-Boltzmann method. So when you have like several components, then you have different properties of the fluids, and that one of the differences is usually a viscosity ratio between them. So different viscosities. And so how technically that works is that you define such a function that is dependent on the order parameter, where you define the bulk phase viscosities, and then you're just interpolating between those two. And like the most simple model that people actually also use in production is like such a simple binary fluid model. In the end, there are certain rules you have to follow that your simulation will be stable, but I'm gonna spare you with all the details. The key point I need to make here is that now your free energy density has like two variables it depends on. And when you have like, you need to define how you want your variables to evolve with time. Like for the density, we already are given this equation by like using the lattice-Boltzmann method in the end. But like for the order parameter, because it's our construction, we need to define how we want it to evolve. And there are several choices. Again, I put the equation here, which is a simple advection diffusion equation. That's all the details for that are actually following in the next talk. But like this equation is a Cahn-Hilliard equation, and it just basically states that your order parameter will move with the fluid flow, and there's like some numeric, or in the end, this diffusion term is more a numeric thing that actually also makes this method quite hard to parameterize, but you need it for stability reasons. And like, so in the end, what you technically need to do is with the multi-component flow is that you actually need to solve two partial differential equations at once, not just your the Navier-Stokes equation you're doing earlier, or you simulated earlier with for the fluid flow, but this time you also need to deal with the the time evolution of the order parameter, which in this case is solving such an advection diffusion equation, which it's your choice how you do that. You can use the lattice-Boltzmann method for that too. There's also other methods, as I said, that are following in the next talk. Like that's all I wanted to show you with the free energy method. Like the whole point is that this model is by construction thermodynamically consistent, which is not the case for all the models. A key point for the free energy method is that it's like a benefit, and that it literally only includes what you put in. You define what you want your system or how your system to behave. But like the parameterization is because of, at least for the multi-component flow, might be a little difficult. But actually a really nice thing is that you have a decoupling of the interface width and the surface tension. The reason that is important is because the interface width will determine your numeric stability of your method. And not all methods allow you to choose them independently. So you're relying on a smaller set of parameters you can simulate. With that, I'm done and want to go to the Shan method, which is actually the most prominent model out there, like within the lattice-Boltzmann framework. It's a so-called bottom-up approach. I try to motivate a little bit why. So the key idea in this method is not that we start with defining a free energy, but we go to the very molecular scale, so to say. And basically, when we look at such a density plot here, then from a molecular perspective, then if you have like some molecules here and some molecules sitting in the respective bulk phases, then in the idea in this model is that somehow we want to separate them because we want to have the different phases. So somehow there must be a repulsive force between those 2 points. Like if there wouldn't be a repulsive force, then they would just like equalize to a common constant density. Like in the end, it's like the free energy, like the ideal gas contribution. So because we have such a separation we're seeking, we expect a molecular repulsion, and this is basically the fundamental idea. And all we're just doing in this model is somehow translated on the restrictions we have from the given grid, as well as the densities, like the quantities we have, because we're not working with molecules but with densities. And so for the simple case of a multi-phase fluid, we basically introduce an interaction of the fluid density with itself. That's the key point. Like I put you the equation here. It looks a little bit ugly, but the effective point is that at every grid point, you're calculating a force that is based on all the densities around that cell. And like if there are gradients within this region, then you will get like repulsive forces. And this is actually all that is necessary for this model to work. And it already gives you reasonable results. For like I said that you're using densities, it's a little bit cheating, so to say, to just use densities, because this psi here is in the end a scaling function. They call it effective density because you run in a lot of numerics instabilities because of the equation of state of your lattice-Boltzmann method. And so in the end, like a really common choice is such an equation here. In the end, it just makes your like your force saturate to basically a maximum value, and yeah, it just improves your numeric stability a lot. Yeah, so for this model to work, you're simulating a single lattice-Boltzmann fluid, and you just need to calculate a local force that is already implemented to like in your regular lattice-Boltzmann method. So you literally need to do nothing. You just need to calculate a force. That's why this model is also so popular. And like to parameterize it, like this, there's like a factor in there, like a g. All the others are like lattice-related things. And what it basically does is like a scaling factor for your force only. And if you exceed a certain value of that, then you just see the separation happening with to the different phases. Yeah, I mean, I will talk a little bit on the drawbacks in a second, but like this whole idea with the repulsive forces is is basically transferable to the multi-component version too, because in there you literally do the same thing, but not just the fluid with itself, but just with the density of another fluid. So technically, you're now simulating two lattice-Boltzmann fluids simultaneously on the very same grid, and you're introducing, like, the only coupling point is a force that you're calculating between those two. And like to parameterize such a system now, again, the only thing you have to do is to fix the prefactor of that force calculation. And usually the quantity you want to match physically is your surface tension. But like I mentioned it in the for the free energy method already, since like you have only one parameter for this, you are coupling your interface with your surface tension, and that severely restricts your applicability of this model. Like in practice, like these are like a two component simulation, and you basically just see that for different factors between those two, you basically see these different curves, and you see the width of this interface changing, as well as some other things. It's a highly a highly coupled parameter in the end to the simulation, which just makes it really hard to control in the end all the different quantities you might be interested in. So for the Shan model, like what I can mention is that it's basically the go-to choice for a lot of the researchers, because it's a very simple model. You basically get it for free, so to say, if you already have a lattice-Boltzmann implementation. And the parameterization is, so to say, really easy because you just match your surface tension. But that also comes with a lot of drawbacks that I already mentioned. And actually, I also didn't talk about that before, but it's something that always comes up within the Shan model. Something that is called spurious currents. So I stole a picture here where that's trying to be depicted. In the end, it's like if you have because we're working on a lattice in the end, and you're the grid, or you have a grid that is obviously a square or like cubes, and you're trying to build a round object around it or in it. In the end, you have discretization artifacts, or you will have them, and calculating gradients on those are always there are always some errors in there, and you're choosing the best you can with the limited set of points you have. Like but that always introduces like some error. And the way this method is constructed, that will just lead to inaccuracies that will cause a fluid flow, even if the simulation itself is in equilibrium, so to say. Like it's stable, nothing moves anymore, and you still have fluid flow. Like that is that's a phenomenon that is present in all the models, but it's very dominant in here. And you will just observe such circular flows in the end on curved surfaces. That's what I wanted to mention with this. Yes. And the last model I want to talk about is, or I will keep myself a little short because it's the most complex one, is the color gradient model, which is technically also the oldest one within the lattice-Boltzmann framework, but it had a lot of initial problems that made it unusable, so to say. And it's a model that this time doesn't have a multi-phase version. It can only be used to multi-component. And the key idea is that this time we're not working with forces anymore, but we try to put all the physics we want to in extending the collision operator. So in the end, it's also a model that is basically restricted to the lattice-Boltzmann framework. The other two are technically usable elsewhere too. Nobody does, but it could work. For the color gradient model, it doesn't. Like it's specifically built for lattice-Boltzmann. And in the end, we are replacing our regular collision operator you saw before by some more complicated construct that is actually a two-step collision operator. So I will go into a little bit of detail on how these these collision operator work. But for that, we need a property that is also given the name, which I put the equation for here. That's usually called a color gradient, and it basically plays the role of the order parameter I mentioned earlier in the free energy model. So it's like these subsets are red and blue, or they correspond to red and blue, and this quantity is just giving is stating to you if you're in a transition area and or not. So this vector will be 0 in the bulk phases and only exist on the interface. And we use that quantity to basically construct or include the properties we're looking for in that system. And for the collision operator, I mean, I already said that it's a two-step one, but it still contains the collision operator we had earlier from to drive it into equilibrium. But there's two additional ones that are called perturbation and recoloring that I will quickly describe here. So for the perturbation operator, it's the operator that actually introduces you the surface tension into the system, and it as a collision operator, it directly acts on the populations itself. And in the end, what you're actually doing, if you're imagining a blue fluid phase and a red one, then you have the color gradient at the interface. And what you're now doing is you're taking the populations and you're perturbing them, you're basically moving them in a physical sensible way, such that you introduce the contribution you want that is coming from the surface tension. I mean, the technical details here, it's it doesn't really matter. They are just chosen. People spend a lot of thought into this to make it physically sensible. It depends a lot on the lattice you use, but all it basically does is redistributing the populations such that you get the pressure tensor or the surface tension contribution into your pressure tensor. But it doesn't actually care whether or not or specific fluid phases are present. So this operator itself doesn't cause any immiscibility. It will just move some populations around. And to actually make the fluids immiscible, you need this recoloring operator. And that is actually also the main reason that this method failed in the beginning. because it caused a lot of problems. But like this formulation here is now what is the one accepted in the community. In the end, it just allows a certain, or like this diffusive interface to build, and it just makes sure that in the blue fluid phase, the blue populations are the majority, and in the red one, the red populations. So in the end, it's just coloring populations, but it's doing that in a clever way too, that it's physically sensible. And yeah, this this model in itself also has like the neat property I already mentioned, that it allows you to specify basically the surface tension and the interface width independently. And yeah, let me quickly summarize that model too. Like I mean, I only scratched the surface of it, but the key point of that color gradient method is that it has like compared to the other models, like a really high numeric stability. But it's I would claim rather complex to implement, and it's also like the main reason people use it in the end, because it's not as versatile as the others might be with coupling to other methods, but really that you can push down your interface to very few lattice sites is more or less something that the other models will get really big trouble with, and the color gradient method is something that can work with that. So like to give you like the idea, in the end, what you're for parameterization of such a model, you would just effectively take the surface tension you want for your system, and then you just shrink your surface up to the point your simulation fails, so to say, and then you get that's usually the workflow people go for, because then you get the least artifacts that stem from this diffusive interface. And yeah, that's in the end all I tried to tell you, or to scratch the surface of this multi-phase modeling. I mean, I introduced you some, and I wanted to briefly mention or dig into the zoo again, that when you now would ask me the questions of now when do I choose what, then I don't have an answer. I can state it's complicated, but it really depends on, in the end, what you're looking for. Usually people start with the idea of, I want to simulate multi-phase flow and I have a lattice-Boltzmann solver. Then your go-to way is always start with Shan, and that's probably also why it's the most prominent model out there, because it gets you very far usually, and it will start to like bring you, or like get you into trouble if you are coupling it to other methods too. That doesn't, or you will see that in a second, but that also goes with coupling it to particle motion. And yeah, then you basically go on, and like if it doesn't work, then you can go, for example, to one of the more complicated models, I would say, that might give you the thermodynamic consistency you want, or if you're just looking for getting the highest like the largest system simulated, so to say, on the largest length scale, then usually a color gradient method is the go-to way, because you can really push down the interface to very few lattice cells.